I'll make you the co-host. It is enabled.
Okay, very good. Okay, and welcome everyone to this rate splitting multiple access webinars. We have the pleasure today to have our colleague Zhaohui Yang from Zhejiang Universities. We'll be talking about RSMA. Just a few housekeeping minutes. So the first thing I would like to advertise is we have two events coming. So we have two special call for papers actually coming up. So the first one is on rate splitting multiple access for future green communication and networks. This is in IEEE transactions on green communications and networks, so TGCN. So for more information, you can go to the RSMA website events and then click on special issues, or you can go directly to the IEEE websites of the transactions on green communications and networking. The other call for papers is for ICC 2024, where we're going to have a workshop on RSMA. And for all information, you can go to the RSMA websites again. You can type this on Google also, rate splitting multiple access special interest group if you don't have access to the website, and you will find it on Google. Okay, so with this, let's move on to today's talk. So today we have the pleasure to host the third webinars in our third series of or third season of our RSMA webinar. So this will be the talk will be given by Zhaohui Yang, with whom we have worked together quite a bit on this topic. So Zhaohui is a well-known figure in our community. Is professor at Zhejiang Universities. He worked on rate splitting, joint communication sensing, computations, federated learning, and semantic communications. He received a number of paper awards, including the Marconi Prize Paper Award this year. He's been very active in the community as an editor of various journals as well. And today, Zhaohui will be talking about application of rate splitting multiple access. So importantly, the talk of Zhaohui will be roughly 50 minutes. You all will be muted. Please feel free to ask any questions. You write them in the chat directly so that actually we can raise them up at the end of the talk, or you will have also a chance to at the end to actually unmute yourself and then ask the questions directly to Zhaohui. Enjoy the talk, and thank you very much for attending. And I leave the floor to you, Zhaohui.
Yes, Professor Bruno, deep thanks.
Okay, so I think you should be able to share your screen now.
Okay, yeah, sure. Okay, can you see my screen now? Okay.
Yes.
Okay, thanks so much. Okay.
Can you
Hello.
check? Yes.
Yeah.
Excellent. Thank you.
Good morning, good afternoon, and good evening, everyone. Well, first of all, thanks so much for Professor Bruno for giving me such a great chance to discuss our recent work about RSMA with the emerging technologies. So the topic of my presentation is about the interplay between rate splitting multiple access and emerging technologies. Okay, this is also work with a lot of people. If you have any question, you can ask me at any time during the presentation. Well, okay, the presentation includes the following 5 parts. Yeah, first is about research background. Just Professor Bruno said there are many chances about rate splitting special issue, journal, and conference. So, if what is RSMA and why we choose RSMA? The challenges of a current access scheme is about, for example, for OMA, it has the high capacity for and the low interference, but the spectrum efficiency is low, which cannot supply massive connectivity. So OMA will be limited in the future wireless network. For NOMA, about non-signal multiple access, it has the ability to connect multiple users, but the computation capacity is high, which is because the efficient use of multiple antenna. So to fully exploit the advantage of multiple antennas, the restricting multiple access is proposed, which is a robust scheme. Take a very small example that the conventional NOMA can be a special case of RSMA. So the RSMA is more general. So the optimization of or the design of RSMA can achieve or have a greater potential than the other access schemes. Okay, that is why we choose resplitting. Well, since we have the basic knowledge of RSMA, so what is downlink RSMA? In the downlink phase, the base station, this is some basic knowledge. So the base station will use resplitting. So it splits the message into two cases, which is a common message and a private messages. The common message is that the message that a subset or multiple or all users need to decode, while the private message is only a small number or only one user want to decode. By using a common message and a private message, each user uses the successive interference cancellation as in NOMA, and so the which user uses SIC. Different is that in NOMA we do not have common message. So in RSMA we have the common message, which is intended to multiple users. But in the downlink RSMA, the total number of messages is higher than NOMA, so we can fully utilize the common message to balance the interference and the desired signal, which can increase the performance gain. Okay, since we have now the downlink RSMA, so what is the uplink RSMA? In the uplink RSMA, similar to the base station split message, in the uplink side, each user splits the message into two parts. So why do the user needs to decode the message into two parts? The reason is that if we, each user splits the message into two parts, so the base station can receive twice a number of users of the messages. So the base station can have more degree of freedom to decode the messages in the order. So the SIC can be fully utilized. So the decoding gain of uplink RSMA is the main performance gain. Okay, in the information theory, it states that each user only needs to split the message into two parts. Then the capacity bound can be achieved in the RESP splitting. Okay, this is the uplink side. So since we have the basic knowledge of resplitting, well, why do we need to still investigate resplitting multiple access? That is because with the development of wireless communications, we are facing many challenges. For example, there are three main challenges that we need to face. The first is that for the smart factory and so on. We need have many users in the network, which not only includes the phone, also the sensors. So we have multiple devices to access the network. Second is that in the future, we will want to discuss or we will have a Zoom meeting with us in the 3D. So the data rate will be much higher than we have in the current 5G and beyond. The third finding is that for the high application demand, we all know that intelligence is one main trend in the future communication. So the intelligent task will be more complicated. So how to utilize desired signal and the interference control in our physical layer to adapt to the above three challenges. To do so, we can use the RSMA system, which means that we can use the RSMA, the good nature or good characteristic to balance the interference from multiple users. So we need to manage the interference in a good manner. So RSMA is a very good technology. Well, how to transmit extremely high rate, in particular 3D video, we can use the rate splitting multiplexes with the semantic communication, which can directly use the video compression technology with RSMA. Then the 3D video and the other high rate tasks can be meted in this technology. Okay, to meet the deployment complexity of the high intelligent applications, we can use RSMA with emerging applications such as the mode splitting and the rate splitting that can be combined to deploy a complicated model in the future applications. So in the following three parts, we will discuss rate splitting in these three ways. Okay, in this part, we'll talk about rate splitting matrices with reconfigurable intelligent surface as a RIS. How? Yeah, I think most of us know about RIS. RIS is a smart or metal surface equipped with low cost and passive elements. Yeah, the reflector doesn't perform or decoding or digital operation, which means that it is a very low cost. Well, the motivation is that we can further improve the energy efficiency of RSMA. We can consider rate splitting with a reconfigured surface. RIS can be used to control the channel of the environment, and the rate splitting can greatly balance the interference and the desired signal. So the combination of RIS and the RSMA can result in very good performance. Okay, this is the work about consider a downlink meso system, which means that the base station is equipped with multiple antennas, and the user is a single antenna, but with multiple users. And we also consider multiple RIS, since the users are distributed randomly. So we need to consider multiple RIS to coverage to have a good coverage of the system. Okay, the transmitted signal of the base station is have the more than the number of users, which means that we have one message for a common message. That means that we have S0 in the downlink for the common message. Yeah, due to the fact that multiple users have want to receive the private message, so each user can have the private message. So in the downlink, the user is to transmit the number of users plus one kind of messages to all users. Okay, at the receiver side, due to we have multiple recombinant surface, so the received signal of the user K is the desired signal. The S is the transmitted signal from the base station. So we have this part GK plus the sum of L equals to 1 to from L to 1 to big L, which is the channel gain from multiple recombinant surface. Okay, have this receive a message. We can use some notations to simplify the notation. Because we have too many surface, we can use the big theta to replace the sum. Then the signal receive equation can be simplified. Okay. From the transmitted signal, we know that the message from the common message S0 here is decoded first. Yeah, this is because we want to perform successful interference cancellation. So the common message, which is intended for here, is for all users. So we decode the common message first. Yeah, based on the receive equation, we can have the common message expression of the CK. Okay, since the common message can be successfully decoded by all users, we should have that the minimum common message rate is the desired common message rate that all users can successfully decode. Yeah, in the common message, we can divide or we can allocate the common message to multiple users. So we have the sum of AK, which is the AK is the part in the common message that is allocated to user K. Okay. While having decoded the message of a common message, we can have the rate of user K for decoding its private message SK. Yeah, since the S0 is decoded, so we can have the rate expression as RK. Yeah, here we do not have the interference from the common message because it is successfully decoded first. So the rate expression of the private message SK can be obtained in this equation. Well, since the rate of each user includes two parts, common message part allocated to user K and the private message part, so the total message of or total rate of user K can be formulated as AK plus RK. This is the difference between RSMA and the conventional OMA or NORMA, which means that the rate of each user includes two parts, the common part and the private part. Yeah, although we have the expression in common part plus a private part for the optimization, we can have that AK is 0 due to the different channel gain settings. So RSMA is a robust or a general case which can include multiple many complexes scheme. So RSMA can be due to the general of this scheme, the gain can be obtained due to a large optimization space. Okay, so the power consumption of the system can be obtained by transmitting the power of the base station due to the circuit power of the system. Okay, yeah, having obtained this above system mode, we had formulated our optimization problem, which is the energy efficiency optimization problem. Well, for the objective function, we can see that this is the total rate of all users, and this is the total power consumption of the system. So the rate divided by the power is the energy efficiency. Yeah. The first constraint is the common rate allocation constraint. Yeah, to ensure that all users can decode the common message. So we need to ensure that the rate allocated to all users in the common part should be no larger than the common message CK every each CK. Yeah, this is the second constraint is the minimum rate constraint for user K. Yes, we have considered the reads. The passive reads is considered here, so we only optimize the phase shifter. Yeah, this is the maximum transfer constraint. Yeah, to solve this problem, we can see that it is highly non-convex, and the both of the function and the constraints are non-convex. It is hard to solve it directly, so we use the SCA plus iterative, which means that with fixed performing and the rate allocation vector, the phase is still non-convex, but we can use the successive convex optimization to solve the phase shifter. Yeah. In the second step, with the obtained phase shifter, we can also use the SCA to obtain a suboptimal performing vector and rate allocation vector with the fixed phase shifter. Okay, through iteratively performing the steps 1 and the step 2, we can obtain a converged solution of the system. Yeah, here is the obtained simulation result of energy efficiency. How the energy efficiency changes with the minimum rate demand. We can see that the energy efficiency first doesn't change and then decrease fast as the increase of the minimum rate demand. This is because when the minimum rate demand is low, since the rate constraint is not higher, but the optimum energy efficiency can be obtained at a level if the minimum rate demand is not that higher. The the maximum energy efficiency is also obtained. So the energy efficiency doesn't change for the small minimum rate demand change. However, when the minimum rate demand changes, since the energy efficiency, the increase of the rate demand needs to increase the consumed power. So the energy, the power is large, then which decreases the energy efficiency of the whole system. Well, compared with normal and off-dimming, we see that rate splitting outperformance conventional schemes in terms of energy efficiency, and the performance gain is high, especially for high rate demand. Okay. In the previous slide, we see we discussed about the rate splitting with reconverted surface, and we only consider the which means that we consider reflect. Yeah, since reflect only can cover half of the users. For the users that behind or blocked by the reads, we cannot also cover or cannot serve them. So we can use the intelligent omni surface or the simultaneous transmit and reflect reads to edit the RSMA, which means that the surface can be each element in the reads can be reflect or refracted. Yeah, we have two modes to choose. We can use it to reflect the signal, or we can use it to transparent it or reflect the signal. Yeah, since we can use the RS to serve two kinds of users, the users in the left hand side and the users in the right hand side. Yeah, to serve these two kinds of users. Yeah, each RS element can choose the function of its element. So we have more optimization variables, which means that we can optimize the function of each RS element, yeah, which first choose each element to reflect or refract. Then we optimize the phase shift of the RS in the reflect or refract function. Okay, based on this kind of IOS, we can formulate the optimization problem as the maximum optimization problem. Okay, which means that we optimize the fair rate, the maximize the minimum rate of all users. Okay, yeah, this is the objective function, and we also consider multiple objective functions. The first is also the common message rate allocation constraint as in the previous slide. Yeah, in the common message, we also allocate the common message part to different users. Yeah, since we consider both common message and private message, so the some transmission power includes the W0 common message power and the W1 to WK private transmitted message power, and the sum power should be limited. Okay. Yeah, to ensure the minimum rate constraint, we also consider the constraint of each user here. The private message allocated for user K and the common message plot allocated to user K should be no less than the desired rate. Okay. Yeah, in here we consider the also to ensure the SIC order was considered SIC order and constraint here. Yeah, the AK should be positive due to the rate cannot be negative. Okay, yeah, beta is the additional variable in the iOS compared to the conventional RS. Yeah, we use beta to indicate the function of this two kind of race. Okay, from the simulation, we have two simulation figures. In the middle figure, we obtain the maximum or the fair achievable rate versus the maximum transmitted power of the base station. From the figure, we can see that for the non-iOS, which means that it's the conventional RS, which only has the reflect function. For the iOS, we have both reflect and the refract functions. Okay. Compared with non-iOS, the proposed iOS can achieve a higher achievable rate, which means that the dual functional or the iOS can achieve a higher maximum rate compared to the only reflect non-iOS surface. Okay, yeah, we also compare the rate splitting with the SDMA. Here in the SDMA, the rate is almost fixed because in the SDMA the interference is not well considered. Yeah, which means that the common rate is 0. We also compare the RSMA with the NOMA and other conventional scheme. It can be obtained that RSMA can achieve higher maximum achievable rate when the in particular the transmit power is high. Okay, in the left hand side of the figure, right figure, we can show the maximum achievable rate changes versus the total number of elements. Yeah, when the elements number of elements is high, the maximum achievable rate is higher. Okay, and the else elements can provide the extra special degrees of freedom to improve the combined channel quality. So it's helpful in improving the rate and improve performance. Okay, in the previous slide, we consider only the one hop or transmission. Yeah, in the receiving, we have to decode the message of common message and private message here. Rate for each user. The formulation. Okay. Okay, thanks for the suggestion. Yeah. Since we only consider the system model first, and we also do not talk about details. If you are interested in the detailed formulation, and we can discuss offline, or for the most interested formulation, I can explain in details. Yeah. Yeah, in this work, we only consider the risk-added cooperative RSMA, which means that we consider two hops in the two phases of transmission. Yeah, in the direct transmission phase, the conventional the base station transmits the common message plus a private message to both users 1 and users 2. So you receive the signal Y K. K means that user 1 or user 2 in the first phase. In the first phase is YK 1 equals 2, and a channel due to the reads, and times the X is the transmitted signal of the base station, includes two parts, common message part and the private message part. Okay, this is the direct transmission phase. Since user 1 is near to the base station, so the channel gain is higher, so user 1 can decode the common message very well. Yeah, to improve the decoding performance of user 2. So in the cooperative transmission phase, user 1 forwards the decoded common stream S0 to user 2 for which means that the strong user helps the weak user in the second phase. Okay, to consider this cooperative RSMA with RS, we formulated the optimal problem as the in the top right. Okay, yeah, because we have the common message C11, means that this is the transmission, this is the common message rate of user 1 to decode the common message in phase 1. Yeah, for the weak user, the common message rate have two parts, and which means that the first part is C21 is the common message rate in the first phase, and plus the C22 means that the common message rate in the second phase, because in the second phase the strong user transmits the decoded common stream S0 to user 2. So the common message rate of user 2 is C21 plus C22. The sum of this here is due to we use some decoding scheme. Well, because the common message needs to be successfully decoded by all users, so the RC is the minimum common message rate among the two users. Okay. In this problem, we also consider the fair and the fair rate. Yeah, we maximize the minimum rate of these two users. Okay, to optimize the performance, we try to optimize the power allocation of power to transmit the power, and also the rate allocation of common rate, and we also optimize the phase shifter of the reads, and we also consider the beta of the which controls the time division of the first direct transmission phase or the cooperative transmission phase. Okay. Yeah. For the constraints, we consider the following 5 constraints. The first is the common rate allocation. Yeah, A1 is the common rate allocation to user U1, and the A2 is the common rate allocated to U2. Yeah, the rate should be non-negative. Okay. Oh, this is the theta is the phase shift matrix. So we have this equation, and the theta changes from 0 to 2 pi, and this the last constraint means the transmit power should have a limit. Okay. Yeah, to solve this problem, we also use the SCA plus iterative. So the details are not provided here. Okay, for the simulation, we consider this sitting at base station, and the location of race is 40, 10, and the locations of 2 users, and the near user is 40, 0, and the far user is 60 at 0. Okay. Yeah. In this setting, we can obtain the following 2 figures. The first figure is the maximum mean rate versus the SNR. Yeah. From this figure, we can see that the maximum rate change increases increase of SNR. This is obvious since the increase of power can increase the failure rate. Okay. Yeah, by using the RS-aided cooperative RSA model compared to the non-cooperative RS, we can see that the maximum rate of the system can significantly increase. Okay, this is the gain obtained from the cooperative transmission. Okay, yeah, from the right figure, we obtain the maximum rate changes as the number of the RS elements. Yeah, with the increase of RS elements or scheme, the rate of all scheme increases fast. Okay, and the rate gain of RS added cooperative splitting RSMA over the RS added RSMA decreases as the number of RS elements increases. This is because when the number of RS is very large, then each system can have the best performance. So the gain of cooperative design is limited. Okay, in the previous slide, we only consider the passive risk, which means that the risk only reflect the signal, doesn't try to amplify signal. Okay, here we only consider the active risk added RSMA, which means that the risk can also reflect and amplify some part of the message. Okay, well, since we consider the active risk, so both the base station and the active risk power constraints are considered in the system model. Okay, yeah, the some rate is considered. Yeah, this is the same as our system model. Okay, we only consider the force the constraint, which means that this is the PA max, which means the maximum constraint of the risk. Okay, this is different from the conventional risk. Passive risk doesn't have any power constraint of the risk, and since we consider the active risk, we consider the PA and max constraint here. Yeah, due to the active risk, and we have different SIR equation here. Okay, this is the common message SNR of user K. Yeah, here we have HK W0 in the first in the front, and for the interference, we consider the interference from private message, and also we need to consider the noise introduced by the active read here, and also we consider the receive noise at the user. Okay, so this is the difference that introduced by the active read. Okay, similar to the common message for the SNR gamma PK of private message at the user K. The SNR also, the interference includes the private message from other users plus the noise amplified by the active reads, and and also the noise at the user side. So yeah, different from the consider this difference in the SR equation, and consider the power constraint of the IRS. We formulate the sum rate maximum problems with the active reads added RSMA system. Okay. Yeah, this is our simulation. Yeah, in the first figure, we showed sum rate versus the total transmitted power. We can see that the sum rate also increases the increase of total transmitted power. Yeah, and that the active reads added RSMA can achieve the best performance, and compared to the active RS, even active RS added SDMA can achieve a higher sum rate than the passive added RS. This is because the active reads can amplify the power of the reflected signal. So the performance of active reads added system is always higher than that of non-active RS. Okay. Yeah, and compared to the passive reads, the sum rate of active reads can increase up to 45 sum rate. Okay. In the right figure, we also show the sum rate changes as the total number of elements increases. We can see that the sum rate first increase fast and then increase slowly as the number of reads element changes. Yeah, the active reads added the RSMA also achieves the best performance. And if we want to achieve similar sum rate, we can see that the required to achieve the same performance, the required number of RS elements can be greatly reduced if we compare it with the passive reads. Yeah, the active reads can only require a small number of RS elements to achieve the same performance of passive RS. Okay, in this part, we consider about the read splitting with semantic communication. Okay, well, yeah, to discuss this basic idea, we first introduce some basic knowledge of semantic communication. Okay, to talk about semantic communication, we first see what is the conventional transmission. Yeah, in conventional transmission, if we want to transmit some bits A here and over the wireless link, yeah, we in the receiver side, we only want to recover the bits that is almost the same, or we can see that is a copy of the transmitter side A. Okay, yeah, the goal is that we want to copy what is transmitted at the source. Okay, yeah, to in the conventional transmission, we want to do it correct, have with the low error rate, and transmit it as fast as possible which means with low delay, and also we want to transmit more as possible. So we transmit want to transmit with high throughput. Okay, this is the goal or design of the conventional transmission. Yeah, in the goal-oriented or in the task-oriented semantic communication, if we have many bits A 10010 to transmit, yeah, since there are too many bits to transmit, and the wireless bandwidth are limited, we cannot transmit so many bits over the wireless. Yeah, so we want to compute the semantic information first, which means that we transmit a small size B here. Then the small size bits B can be transmitted over the wireless link. So the receiver, when it receives the bits, then it can try to understand or try to infer the information that behind the message of received bits B here. Here with semantic communication, the semantic information which can be the context or semantics or features that are related to the decision or the goals of the receiver. Yeah, from the transmission process of semantic communication, we can see that we do not want to receive the copy of that the receiver or the transmitter wants to transmit. We want to transmit small size information, which means that we can have high efficiency. Then the required wireless resource will be small. The second property is that the whole system can be can have a more have high security. This is because if we want to recover the message that behind the received or bits, we need to have some common we have some common knowledge. We know how to infer or how to understand the information behind the received small size bits. So the security can be enhanced because only the receiver knows something before, then it can recover the information behind the bits. Yeah, the last advantage is that semantic communication can be unified to many systems because we only transmit the information related to the task. So any different system or many human to machine or machine to machine can communicate with each other. Okay, yeah, with the understanding of semantic communication, we know that both the transmitter and the receiver needs to have some common analysis, knowledge. So the transmitter can transmit small size semantic information, and the user can understand the semantic information because both transmitter and the receiver have the same or similar common knowledge. Yeah, in reservation, as we talked before, we have the common message and the private message for each user. So if we combine readability with semantic communication, because in semantic communication we need to transmit the common knowledge to all users, while in the readability, common knowledge is also shared by all users. So we can use this pure maybe a good match of readability with semantic communication. We can use a common message to transmit the common knowledge, and the private message to transmit private semantic information. Then the whole system will be more robust and with high efficiency. Okay. This is our detailed system model. Yeah. The transmitted signal acts as the base station. It can be expressed as this formulation here. Yeah. x equals to W0 as 0, which means S0 is the common message for all users, and the W0 is the performing for the common message, and the plus the sum is the private message part with WK standing for the performing vector for private message SK. Okay. Yeah, with the transmit signal at the base station, the receive signal at the user K can be expressed as HK X plus NK. Here, the HK is channel gain between the base station and the user. Well, yeah, based on the received signal equation, we can obtain the rate expression for the common message SK of user K, which is the common message rate of SCK. Yeah, here we consider the rate common rate allocation for all users here. Yeah, different from the general. It is also rate splitting, but let's say scheme. Yeah, as we previously reported and discussed with Professor Bruno. Yeah, here, yeah, A0 is the message that all users need to or all devices need to decode. Yeah, is the A0. Yeah, and the AK is the part that's allocated to the user K in the common message part. Yeah, because we have the common knowledge that is shared by all users, so we can have the time for TO for the common knowledge. Yeah, TO is the time that all users need to that is the time that all users share to decode the common knowledge. Okay, and since the private or the rate for user K includes two parts: the common rate plus the private rate RK plus AK. So the time for private semantic message intended for each user is TK equals has this formulation, because the rate of private semantic message is RK plus AK. Okay. Yeah, based on the above system model, we can formulate the optimization problem of the total energy minimization problem. Yeah, such considering such blah 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 constraints. Yeah, the total energy here E includes two parts: the transmission part for the wireless transmission and the computation part, because we want to transmit small size data. Yeah, although the transmission time can be decreased, but we need to compute the small size semantic information, so we have additional computational cost. Here we consider the trade-off between the transmission and the computation, because we need to compute the semantic information first, which also consumes time, although the semantic compression can decrease time, but the compute can increase time. So there's a trade-off between the compute and the transmit. The first constraint is about the some time for each user. Yeah, the first Y1K is the compute time of the base station, and Y2K is the computation time of the each user. Yeah, the transmission time is the wireless transmission time, because both the common knowledge and the private semantic information are transmitted simultaneously. So the time is the maximum between the maximum of the common knowledge time and the private message semantic information time. Okay, The second constraint is the accuracy. Which means that although we transmit a small size information, we need to ensure that the accuracy at the receiver side can be higher than a defined or threshold. Yeah. Third constraint is the semantic information selection constraint. Yeah. We also consider the following constraint related to the rate allocation in the common rate. Yeah. Since we have many users, we have many semantic information to compute. Yeah, the total computation resource at the base station can be allocated to different users. We have the sum fk should be smaller than the maximum computation capacity at the base station here. Yeah, we also consider the downlink transmission power constraint. Yeah. Okay. Different from the conventional design here, we only consider the common message to transmit the common knowledge, and the private message to transmit a private semantic information. Okay. For the optimization variables, consider the graph selection, computation capacity, transmit power, with location, and transmit performing. Yeah. Since the transmitted equation can be obtained in dozens or in many Professor Bruno's very outstanding papers. However, for the computation, it is hard to obtain the formulation. So we try to obtain the formulation of the computation cost. So we use the probability graph to obtain the semantic information here. Here we consider the probability graph. I take a small example. If we obtain the IC, we watch the IC building for 100 days, we have some basic knowledge or some static information, that which means that the person in the IC building can wear his hat with a high probability of 0.8, and the hat on the hand of the person in the IC building is 0.2. Yeah, we have this static information because we watch the building 100 days. Okay. But if in the 101 day we want to transmit some information, for example, the hat on the hand of the person, and the person is in right side of the car. Since we know that the person in the right side of the car with 0.6 probability, in the 101 day we can choose to hide this information. Yeah, we only transmit car person. The relationship of the person in the car, we can hide it because we have the common knowledge that the car is in the this person is in the right of the car with high probability. We can infer that information in the receiver side, so we can hide this information in the transmitter side to decrease the communication cost. Okay. Yeah, this is the a kind of the number game. We can hide some number in the transmission, and then we can infer the message due to some loss of the information. The law means that the probability graph that we can use to infer. Yeah. Okay. We hide the information right on the person right on the card. For the low probability, because for example the hat is on hand of the person, can we have the chance to hide this information too? The answer is yes, because we can use the conditional probability graph, yeah, we can have some conditional probability, because for the cloudy today is not today is cloudy. The hand at hand is a high probability. We can have this kind of information. Yeah, we know this kind of information before. So we can use the probability graph to hide some information, which means we can use the probability graph to compress some information, and then the transmitted information after we using probability graph can be increased. Okay, yeah, here we use the transmission time here T1 as the number of hidden bits. However, since we need to do computation cost due to the inference of probability graph, here we obtain the equation of the computation times. Yeah, E1 means that we have m relationships, and Q1 probability with high with high probability that it is larger than 0.5. So we can hide m times Q1 if we use the probability graph first, and E1 elements can be hide. Here, however, if we use the one information as the conditional information, then we can hide m minus E1 times Q2. Q2 is the probability in the with one information as conditional information. Then the number of hidden probability is Q2. So the number of hidden information after we use the one information as a conditional information, the hidden bits can be E2. Use this kind of relationship, we can hide En if we use the conditional probability graph n times. Okay, so E1 to En is the total number hidden bits. Since we need to compute, if we want to hide E relationships, so the number of computation times can be obtained as C1. If we want to we have the had a low number of relationships within that, which is if E1 is less than, if E is less than E1, we can use the times E divided by Q1. This is the total number of condition times we needed to hide E relationships. If we want to increase the number of E, that means we have E is greater than E1. Since E is greater than E1, we cannot cannot to hide the more than E1 relationships. We only run the probability graph one time. So we need to run the probability graph one more time and use additional conditional information. So the total computation times will be two parts. The first part is the time to run the probability graph one time, and the second is the time or the computation cost to run the conditional graph one more time. Okay. Yeah. Due to the above understanding, we can obtain the computation cost of using the probability graph for semantic computation cost. Yeah. Okay. With both communication.
Zhaohui, due to
yeah.
time constraint, I think it would be good if you can conclude soon, because it's already 6 past the hour.
Oh, okay. Sorry.
Yeah.
I will fast. So sorry. Yeah. Okay, we'll go fast here. Yeah, this is our simulation result. You can see that RSMA can achieve a better energy consumption. In particular, the maximum transmitter power is high, and also if we grow the total energy of RSMA is slower than that of normal and FDMA. Okay, and the total energy first decreases rapidly, and then the total energy tends to approach a fixed value with the increase of the maximum computation capacity. Okay, let's come to the part 4 about RSMA with emerging technologies. Yeah, security is an important part of our communications. So in risk splitting, we have the common message as interference. So we can use common message to also serve as the desired message and artificial noise without consuming extra power. Okay, this is the one advantage of RSMA. Okay, the other is that we have the split learning, right? We have the bigger model to configure it in wireless communication system. We can split the model, and this is also similar to the rate. We can split the rate into two parts, or we can split the model into different part, and then we can use this relationship to use RSMA fit transmission of split learning model. Okay. Since the signal in the UAV in the air is not very stable, we can use the robust transmission of RSMA to support the air communication. Okay. Yeah, we all talk about the big AI model. We can use the big AI model to serve the wireless communication for multiple talks and multi scenario and multiple scheduling. Yeah. However, the conventional the NRP big AI model cannot be directly used for solving wireless problems due to the two differences. The first difference is that the location of two apples can be the location can be different, but the meaning of the two figures are similar. However, in the CSI matrix, the CSI will be totally different if we change the delay, the location of the delay. The other difference is that if we have two figures and we but in different time, the two figure in different time can have the same meaning, but the CSI changes very fast even at the same location. So we can use the physical layer process by using rate splitting to the robust transmission to support the design of the AI model for wireless communication. Yeah. Okay, there are some future directions, which includes the theory, optimization, and the experience part. Okay. Yeah. This is our conclusion that the gains of downlink RSMA come from the balance of signal and interference. And the uplink gain comes from the SIC order. And the SIC aided RSMA can enhance performance in some rate and the fair rate and so on. And the RSMA aided communication can best fit the common transmission. Okay. There's also GlobalCom 2023 RSMA tutorial in about RSMA in also the workshop. Okay, yeah, thanks so much for everyone's attention, and also welcome to join the RSMA WTC SIG and discuss RSMA. Yeah, special thanks for the Bruno Clubs for the invitation, and Adin and Wang Jinxin and Lina and Mitra. Okay, thanks so much.
Thank you very much, Zhaohui, for the very interesting talks, and I think you really nailed it with the numerous applications that actually you showed. Maybe we can have one or two questions. I don't know whether we have any questions in the chat.
Yes, there is.
From Yadav, Chotu Yadav. I think, Chotu, would you like to ask the questions directly? It's about imperfect SIC.
Yeah. Oh, it's SIC is perfect, then there is error propagation. Then what challenges raises in RSMA and with RS when implementing imperfect SIC? yeah, how do these challenges impact on performance and security? Okay, thanks so much for Chutu from IIT for this a good question. Yeah, imperfect SIC is a very important or very practical constraint in the design. Yeah, I think many many works in RSMA shows that yeah, RSMA is more robust for the error. The superiority of RSMA is more is obvious in the imperfect CSI. Well, for the robust for the imperfect time again, we can formulate the robust optimization, which means that we try to optimize the worst rate among the imperfect CSI space. So this is the design about robust optimization design. Okay. Yeah, this challenge impact. Yeah, the performance can be is not it will be degraded, but yeah, compared to other schemes such as SDMA, OMA, and the NORMA, and the RSMA is almost is always the best in the imperfect CSI case. This is the answer. Okay, hope this can answer your question. Yeah. So we can go to the.
So maybe we can add also on the SIC. I think in the Anoop, correct me, but actually on the web page, we have there are many literatures that listed.
Yes.
And we have several papers who have already addressed the imperfect SIC. For instance, in the link level simulations, we have imperfect SIC because we have finite block lengths. And so you cannot guarantee that actually streams is always correctly decoded. And there, so it's already investigated, and then the performance gain is still there, despite the fact that we have imperfect SIC in a real system. Right, so I think I would refer to the RSMA webpage there for more information on this specific topic as well.
Yeah, and I have shared the link of the website best ratings page.
Okay.
There's one more issue regarding this by somebody else, so I've shared the website page. One more question from Abid Arif, who is, I think, in slide 13, is asking, please show the formula which you have used for rate of each user to formulate the optimization problem. And he has raised his hand also. So Abid, if you want to ask that question yourself, you can.
Thank you so much, Professor. Thank you for your organization, and thank you, Professor Yang, for your nice presentation. My question is about the second part of your presentation, the related optimization problem for the rate splitting multiple access application. In my understanding, when we are going to formulate an optimization problem for the rate splitting multiple access application, more important than everything, we should take care about the rate of the users, because our strategy is to split the rate of the users to provide the multiple access. Okay, so in the optimization problem, assume that one of the users is communicating with base station through the short packet. As you know, for short packet communications, according to the finite block length information theory, we are unable to use the Shannon's classical formula because it's not a suitable formula to guarantee the short packet communication quality of service. So I just ask, which formula did you use in your calculation? In one of your slides, I saw that the Shannon's classical formula is used in your optimization problem.
Yeah, we use the Shannon capacity. Yeah, this is your question is very good. In the Shannon capacity, we assume that the length of the code can be infinity, right? According to your question, in the actual communication, the code is finite, right? Yes. Although we use the channel capacity because the capacity is our outbound. Yeah, we optimize outbound. Can also have the benefits of using the we optimize the bound, then the actual rate can also be optimized. Yeah, this is one reason. The second reason is that if we use the short package rate expression, the expression will be complicated. We also have the error function
Yes.
in the error function. So the function will be have an integration, right? So the calculation will be complicated. The optimization will be not easy. So we can use the optimization formulation of it.
Okay. I think it's better for such optimization problem. It's better to utilize the formula presented by Professor Vincent Pu in 2010. Yes.
All right. Yeah, I think that Professor Bruno. Okay. Yeah, Professor Bruno also has one paper about rate splitting with a short package.
Yes.
Also Lina. Yeah.
Okay.
Yes, there's some works on this for downlink and for uplink with RSMA with short packets. So this is, I think, also available on the web page.
Yes, definitely, yes. And another point, and my concern is about the difference between the online optimization problem and offline optimization problem. I think your problem and formulation of your problem is stated based on the offline optimization problem.
Yeah. Yes.
So let's say the solution of your problem is correct just for some realization of the channel. And for online optimization problem, I suggest go through the artificial intelligence and and enter the parameter time in your problem to guarantee the online quality of service.
I also agree with you. You can use the offline training and then use the online deployment of the optimization problem. Yeah, because in the RSMA problem, the optimization variables and the number of optimization variables is larger, right? And the problem is more complicated. So using the AI is one of the potential or emerging or good technique to optimize the RSMA optimization problem.
Yeah, and in artificial intelligence, I suggest reinforcement learning for such problems.
Yeah.
Thank you for your nice presentation, and thank you for your organization. I have no further question.
Thank you very much for the questions. So we have Tuyen also actually raised questions on the usefulness of splitting messaging into common and private parts. I mean, this relates to the fundamentals of RSMA. I would refer V to look at the web page again that actually Anup just shared and looked at the best readings there, especially the tutorials on the topics. I think that would clarify a lot of your questions there. I don't see any questions on the chat. I don't see any other hands raised. So I think, oh, is there still a hand raised? No. Okay, very good. Thank you all. Anup, maybe you can say a few words about the next webinar. When will it be? 2 weeks from now, I guess?
Yes, 2 weeks from now. Just a second, let me confirm the date. It's on November 14th.
Right.
Dr. Honur Distar, he's from Viavi Solutions, and he's going to give us an industrial perspective of the RSMA scheme and his work and how Viavi is looking at this rate splitting multiple access.
Excellent.
Yeah.
Thank you very much, Anup, and looking forward to seeing you all then in November, in the next webinar.
Thank you.
Bye-bye. Have a nice day.
Yeah, thank you very much, everyone. Bye-bye.
And thank you very much, Zhaohui, for your talk, of course.
Yeah, thank you so much.
Thank you, Professor Yang, for the talk.
Yeah,
Bye-bye,
thank you so much,
everyone.
Mishra, everyone.